Chapter 10 on fluids has a bunch of different types of problems, most of which are quite easy. I'm going to walk you through all the different types of problems that you might encounter in this chapter. So first of all, there's pressure and depth. So it says you're designing a diving bell to withstand a pressure of seawater at a depth of 250 meters. And we want to know what's the gauge pressure at this depth and what's the net force due to water outside and air inside on a circular glass window 30 centimeters in diameter if the pressure inside the diving bell equals the pressure at the surface of the water. Okay, so first of all, let's talk about the gauge pressure. Okay, so what we know is that the pressure at the bottom is equal to the pressure at the top of the water, which is atmospheric pressure, plus rho GH. Okay, so in this case, the gauge pressure, the pressure at the top is the atmospheric pressure, so the gauge pressure is equal to the pressure at the bottom minus the pressure at the top, which is just rho GH. The density of water is well known. That's 1,000 kilograms per cubic meter. G is 9.8, and we know H is our depth of 250 meters. So we just plug all that in, 1,000 times 9.8 times 250. We get 2.45 times 10 to the 6 Pascal. So that's quite a high pressure. Atmospheric pressure is 1 times 10 to the 5. So this is about 25 times atmospheric pressure. Alright, so that's our answer for part A. Part B, now I need to interpret this a little bit. So what it says is you've got a glass window. It's a circular glass window, and inside the bell, so here's our bell here, inside we've got atmospheric pressure presumably, and on the outside we have the total pressure at the bottom, so it's atmospheric pressure plus the gauge pressure. Okay, so what's the force? Pressure is equal to force over area, so the force is going to be equal to pressure times area. And so the net pressure difference is just going to be the gauge pressure. We've got equal pressure of atmosphere on either side. So net pressure is equal to the gauge pressure. We know that. So we need to find the area of the window. Okay, so we've got a circular window. So the area of a circle is pi r squared. And the diameter is 30 centimeters. So we've got 15 centimeters, so times 10 to the minus 2 meters is our radius, and we've got to square that. Okay, so remember, for a lot of problems in this chapter, when you read it, they're going to give you a circular thing with its diameter. You need to divide that by 2 to get the radius. Okay, so if we plug that in for the area, we get an area of 0.07065 square meters. Okay, so finally find the force is equal to the pressure times the area, and we know both of them, so it's going to be 2.45 times 10 to the 6 times 0.07065, and we get 1.73 times 10 to the 5 newtons. And it's a really huge force. The second type of problem in this chapter has to do with Pascal's principle in hydraulic lifts. So in a hydraulic lift, you typically have two pistons that have a different diameter. In this case, we've got one that's 2.5 centimeters and one that's 10 centimeters. Draw like this. Okay, and we have a car on top of the bigger piston. Okay, and the car has a weight of 10,000 newton, 10 kilonewtons. And we want to know what force do we have to apply here in order to get a force of 10 kilonewtons to lift the car on the other side. So what we know from Pascal's principle is that the force over area on the large piston is equal to the force over the area on the small piston. The area of the large piston is pi r squared. Okay, so the radius of the large piston is 10 centimeters, so we've got pi times 0.1 meters squared, which is 0.0314 square meters. The area of the small piston is again pi r squared, but now we use the radius of 2.5 centimeters, which is 0.025 meters. And we get an area of 1.963 times 10 to the minus 3 square meters. Right. So we've got our two areas. We know our large force is equal to 10 kilonewtons, or 10,000 newtons. So we want to know what the little force is. So if I rearrange my equation, I get this. And now I just plug in my number. So it's 10,000 times the small area, 1.963 times 10 to the minus 3, divided by the big area. And we get 625.3 newtons. And we need to take that to 3 sig figs, 625 newtons. And in fact, since we're doing a ratio of areas, we didn't actually have to convert the centimeters into meters. All right, next topic in the chapter was Archimedes Principle. So Archimedes Principle said that the buoyant force is equal to the weight of the water displaced. So in this problem, we've got an ore sample. We know that its weight is 17.50 newtons. And then when we take it and we put it underwater, its weight is effectively decreased because the tension in the cable now is only 11.20 newtons. So we want to find the total volume of the object, and we want to find the density of the sample. Okay, so we know its weight, so once we've got its volume, then we can find the density. So first we need to find its volume. So how do we find it? Well, the buoyant force is going to be equal to the weight of the sample minus the tension. And so the difference in the apparent weight in the two cases is equal to the buoyant force. So 17.50 minus 11.20, and I get 6.30 newtons is the buoyant force. Okay, and we know the buoyant force is equal to the weight of the water displaced, so that's equal to the density of water times G times the volume of the sample. And so we know the density of water is 1,000 kilograms per cubic meter. We know G is equal to 9.8 meters per second squared, so we can find the volume. So the volume is equal to the buoyant force over the density of water times G. So the buoyant force, 6.30 newtons, divided by 1,000, divided by 9.8, and I get 6.43 times 10 to the minus 4 cubic meters. Okay, so what's the density of the sample? The density of the sample is equal to the mass of the sample divided by the volume of the sample. We know the volume and we know the weight. The mass of the sample is equal to the weight of the sample divided by G. So that's 17.50 divided by 9.8. I get 1.786 kilograms. So put that in up the top, 1.786 kilograms divided by 6.43 times 10 to the minus 4 meters cubed. 2,777 kilograms per cubic meter, so it's about 2.8 times So it's about 2.8 times the density of water. And I've got 4 sig figs, so I'm going to keep 4 sig figs in my answer. So 2,777 is my answer for the density. Okay, the fourth type of problem involves the equation of continuity, which states that the amount of water into one end of the pipe has to be equal to the amount of water out the other end of the pipe. And what that means is that the area times the velocity of the water on one side is equal to the area times the velocity on the other side. So if you shrink the area, you've got to increase the volume. All right, so what I have is I've got a 2.5 inch diameter pipe, and I shrink it down to a 1 inch diameter pipe. Okay. I know that the speed of the water going in is 6.00 centimeters per second, and I want to know what's the speed out. Okay, so area of side 1 is pi r squared. Make sure you know that equation. You're going to use it a lot in this chapter, and you won't be given it on the test. So it's pi times the radius, 1.25 inches squared. In this case, I'm not going to change the units because I'm going to keep it the same on both sides. So I get 4.909 square inches. On the other side, I get pi times half an inch squared. So I get 0.7854 square inches. Okay, so I want to find V2. So if I look at my equation, V2 is equal to A1 V1 over A2. I know V1 is 6. So I got 4.909 square inches divided by 0.7854 square inches times V1, 6.00 centimeters per second. And you can see this looks terrible because I've got all kinds of mixed units. I've got inches, I've got centimeters, and I should have everything in meters, but it turns out it doesn't matter because those inches cancel out with each other. So you get 4.909 divided by 0.7854 times 6 gives me 37.5 centimeters per second. All right, last kind of question involves Bernouilli's law. So Bernouilli's law says that at any point in a pipe, this product is constant. So we got the pressure plus rho GH, let's say rho GY, plus 1/2 rho V squared is equal to a constant. Remember we said in class this is like conservation of energy. This is potential energy, that's kinetic energy. Okay, so we've got 2 points in the pipe. So I've got 1 point in the pipe where I know my speed. So we've got P1 plus rho GY1 plus 1/2 rho V1 squared. That's got to be equal to P2 plus rho GY2 plus 1/2 rho V2 squared. Okay, so we're told P1, we're told the difference between Y1 and Y2 is 11 meters, and we're told the initial speed. Okay, so we've got V1 is equal to 3.00 meters per second. P1 is equal to 5.00 times 10 to the 4 pascals. We're told that Y1 minus Y2 is equal to 11.0 meters. Okay, and that the diameter of the pipe at the bottom is twice that at the top. All right, so what we've got is a pipe that goes down 11 meters, and at the bottom it's wider than at the top. So here I've got R1, and here I've got 2 times R1. So I know I want to get P2. So P2 is equal to P1 plus rho G times Y1 minus Y2. Okay, so I know this, I know density of water, I know G, I know that. Plus 1/2 rho V1 squared, I know V1, minus 1/2 rho V2 squared. I don't know V2, I need to find V2, so how am I going to find it? Well, I'm going to use the difference in diameter of the pipes. Okay, so I'm going to have to do exactly what I did in the previous question. So I've got A1 V1 equal to A2 V2, use the equation of continuity. So V2 is equal to A1 V1 over A2. Okay, now they don't give us what the diameter of the pipes is, but they do tell us that R2 is equal to twice R1. Okay, so A1 is equal to pi R1 squared. A2 is equal to pi times 2R1 squared. So if I square that, I get 4 times pi R1 squared, so I get 4 times A1. So the area of pipe 2 is 4 times the area of pipe 1, and so that means, of course, that the speed in pipe 2 is going to be 1/4 that of the speed in pipe 1. So I'm going to get 0.75 meters per second. When you do Bernouilli's law equation, now it's important that you put all your things in standard units. So your heights have to be in meters and your velocities have to be in meters per second. You can't get away with using centimeters or inches in this equation. Alright, so now I've got V2, so I've got everything. I just have to plug it in. So P2 is equal to P1, 5 times 10 to the 4 pascals, plus rho, 1,000 times G, 9.8. Y1 minus Y2 is 11.0 meters, plus 1/2 the density, 1,000, times V1 squared, times 3 squared, minus 1/2 times 1,000 times V2, which is 0.75 squared. Okay, so plug all that into your calculator, and let's do it by parts. So we've got 5 times 10 to the 4 plus 1.078 times 10 to the 5 plus 4,500 minus 281.25, and we get 1.62 times 10 to the 5 pascals. And this is the gauge pressure. So remember, the absolute pressure in the pipe would be this plus atmospheric pressure. So it'd be something like 2.6 times 10 to the 5 pascals.